any of the lemmas we've proved up to now, 13.6 and 13.7. Okay, queries? Yeah, about that? Okay. So let's go for lemma 13.8 then. Is the next one. Okay, so this is where we're going to establish that second line there. G is the internal direct product of its primary components. So G will be equal to the direct product, internal direct product of its primary components. Remember, G has order n, which prime factorization, product of the p i's to the alpha i's. And it's going 1 to k. 1 to k. And so you've got k of these primary components. Each primary component is what we called a p group before. It just consists of all the elements of G whose order is the power of that particular prime, whatever the index of I is. Okay, so Gi is defined to be, now first of all, the first thing will be to prove it actually is a subgroup, but it's defined to be the set of elements X in G such that the order of X is some power of the prime Pi. Okay, so it's a P group. Or we will call it a P group when we find out it is a subgroup. It is a group. Okay. Okay. Right then. There's just a little bit slight problem with the way he stated this. He stated it where k is the number of distinct prime factors in n. But then he also says it's just unfortunate he reuses k here. So Gi consists of all the elements of order pi to the k for some integer k. But so this k here has nothing at all to do with that k there. This k here is the count of the number of distinct primes that there are dividing into n, but it hasn't got anything at all to do with this power on one of the individual primes pi. I guess it's valid and consistent within just the scope of that sentence that it's in, but it's just unfortunate that it's reused the same letter there. That's why I've used a different one there. So there's a bit to prove here, and the proof makes. Oh no, we're not talking about quotient. Sorry, it's the next lemma further on. The actual lemma that does most of the work. It's splitting off the cyclic component. There we make a lot of use of everything we've got up to now. Factor groups, quotient groups, and so on. And this is just an argument that just goes on within the group G. So it's not too bad. So first of all, we must prove each of these primary components actually are subgroups. Okay. First, we'll show each Gi is a subgroup. At the moment, we just have it defined as a set of elements. We want to show it is a subgroup of G. Okay, this isn't too hard. So how do you prove a subset is a subgroup? First thing you want to do is you want to confirm that the identity is in there. So certainly the identity is present in G as what's the order of the identity? The order of the identity, of course, is 1. E to the 1 is equal to E. But that's equal to 1 is a power of a prime. It's that prime raised to the power of 0. Okay? So the identity is certainly in each of the primary components. Okay, fine. Now let's show that it's closed under inverses. So if G, remember the order of, what's the order of a, so this is nothing particular to do with this is true in general. What's the order of the inverse of a group element? Well, in particular, it's the same as the order of the group element itself, yeah? So that's true in general. You've got any group element, it has a certain order. If it has a finite order, yeah, if it has an order, be it finite or infinite, its inverse will have exactly the same order, okay? So certainly this set is closed under inverses. Whatever elements are in here, their inverses in G are also in there. So then the main thing we have to prove then is that it's closed under the group operation. Okay. So if X and Y are elements of G, yeah. So if GI, say the order of X is P to the, I'll stick with this notation here, P to the R, say, and the order of Y is equal to P to the S. Okay, so we've got two elements, sorry, this is PI. We got two elements whose order is a power of the prime PI. These are elements of, by definition, of the ith primary component. Now, of course, we don't know what R and S are. We don't know what R and S are. They're certainly bounded above by alpha I. Remember, the order of any element must divide the order of the group by Lagrange's theorem. So the biggest that R and S can be is actually equal to alpha I, but they may be smaller. But the question here is now, what's the order of X times Y? But all we need to notice that if we let T. So if you let T be the maximum of R and S, okay, one of them might be smaller than the other one. Just let T be the maximum. Then when you raise XY to the power T, now remember, I'd shoot you down if you did that normally in a group. Right? You're not allowed to do that normally in a group because here this power looks like xy, and you repeat xy t times. Here I've gathered all the x's together and all the y's together. So that crucially relies on the fact you're in an abelian group. So that's okay. In a general group, you're certainly not allowed to do that. You're not allowed to assume that. It might be true, special elements, but not true in general. So that's okay because we're in a finite group. Sorry, not right. Sorry, we're going to raise it to the power of p to the t. So sorry, let's raise to the power of p to the t. Sorry, not t. P to the t. Well, but p to the r divides p to the t, and p to the s divides p to the t. Yeah, because t is the maximum of s and r. So certainly both p to the r and p to the s divide. So that means, continuing on this equation here, that means what we've got here is equal to the identity times the identity. So this is equal to the identity. Okay. Because already in this power x to this power, you've already got x to the power pi to the power r. So that's equal to the identity, and then you're just multiplying the identity by itself a certain number of times, still the identity, and similarly on the y. So that means when you raise x times y to the power p to the t, that looks a bit bad, that whole p to the t is in the exponent position there. When you raise it to that power, you get the identity. So that means that doesn't mean its order is p to the t, but it means whatever order it has, it divides p to the t. Okay, because remember, whatever order an element has, The only way you can get that element raised to some power equal to the identity is if the power is a multiple of that. Okay. So that implies the order of xy divides p to the t. But if it divides p to the t, pi to the t, sorry, that was all p. Keep forgetting my subscript I. It's a subscript I on all these p's. The order divides pi to the power t, so that means it must be some power of pi. Okay? It's the only divisors of pi to the power t are smaller, that power itself and smaller powers. Okay? So the order of xy is a power of p to the I. So the xy is in the ith primary component. Okay. Is that okay? Any queries about any of the steps there? Okay. So it's just detailed consideration of what's going on with the orders of these elements. So that's the ith primary component as a set, but we've now proved it has the identity in it. For any element in it, it automatically has the inverse in it. And for any pair of elements in it, the product is also in it. So that means it's a subgroup. Okay, those are the three conditions you need to check to show a subset is a subgroup. So GI is a subgroup of G. Okay, so now we've got a collection of subgroups G1, G2, GK. So this is potentially something we can make an internal direct product out of. Now, just remind you, in order to do an internal direct product, just write it up here for two factors, but an internal direct product, you need to have subgroups H and K, subgroups of a group G, of a group G, not necessarily just any group. We need to know that the intersection between them is almost disjoint, that they only have the identity in their intersection. And if you can show that for every G in the group G, G can be written as a H times a K, some H and H, little k and k, H and H, little k and k. If you can establish these conditions, then you know that G equals H times K, because everything in G can be written as H times K, and this is isomorphic to the direct product of H times K. Okay, everything in G can be uniquely defined as a product, something from H times something from K. So that's an internal direct product when we can establish these conditions. So we've got a bunch, and okay, this is just for two factors, but it extends to more than two. So we've got our bunch of subgroups now, the primary components. So now we have to prove these conditions, that they're all as disjoint as they can be. So in a pairwise fashion, the only thing common between any two of the primary components, any two of the capital GIs, is the identity element. And secondly, we have to finally prove that anything in our group G can be written as a product of elements, one from each primary component. Okay. That's a little bit which I think he has skirted over or leaves out of his proof, so we'll have to fill that in here as well. Okie dokie. So you'll see here, so we've gotten to the end of here. We've proved that it's a subgroup, which ends here. So now he says we must prove that G equals the product of all of those. So he's really saying, i.e. he's talking about this as an internal direct product here. This expression here. Okay. Now he's using one, actually when you're reading that, I'll stick with using E, but he's using 1 for the identity there. Anyway, just to remain consistent with my handwritten notes, I'll use E for the identity. It's slightly confusing, of course, because you have to be careful. Like this one here is the integer one. That's the power of the prime. This is talking about orders. So that's the integer one. But that one there, 1 in GI, that's the identity element of the group. So it's good, and it's a nice, efficient use of notation, but it can be slightly confusing because you got ones floating around that mean different things. So I'll stick with using E for the identity here. So first of all, so now we want to set up or prove the conditions. Set up or prove the conditions for G as the internal direct product. G being the product over I of all the GIs, which is isomorphic to G1 across G2 across all the way to GK. So the first thing to do is we have a claim that the GI are pairwise coprime. i.e., what that means is a GI intersect GJ is only have the identity element in the intersection whenever I and J are different, whenever you're talking about two different primary components. Now, the way we'll do it is we'll present the argument for that G1 is distinct, sorry, not pairwise coprime, sorry, I said that. Pairwise, it kind of lacks a word for it. Let's just say that's why I'll put it in quotes. This isn't common terminology, but pairwise is disjoint as possible. Okay. Subgroups can never be completely disjoint because they must overlap in the identity, but as disjoint as they can be. And it's kind of a so to understand what he's doing here, he's actually proving something slightly stronger. So we suppose, suppose an element G1, so G1 is some element from the first primary component. So it's some element whose order is power of P1. Suppose an element G1 was in the subgroup generated by the other primary components. Okay. So if you take all the elements of the other primary components, mush them together, allow them to generate a subgroup. Okay, so this would be the smallest subgroup of G that contains all of these. Well, suppose that's the case. So, i.e., that means our G1 can be written as a G2 times a G3 times all the way up to GK, where each GI is in capital GI. Now, this really can't happen, okay? It can only happen, what we're going to prove, it can only happen in the special case where G1 is the identity element. That's what we're going to say, okay? And that will prove that G1 can only overlap with any of these in the identity element. Okay, let's just prove it first, and then once we see it, we'll fill in it, or we'll emphasize the details. Now, remember, for every value of I between 1 and k, each gi has order a power of pi. Okay, now in the book he said pi to the alpha I, but it's not necessarily that. So has order pi to it's just a matter of choosing a letter for it. So alpha I is already chosen because we specified alpha was the exponent of the prime pi and the prime factorization of n. So it's alpha I is the largest this exponent could be. Let's call it a gamma I. So each gamma I is less than or equal to the alpha I that appeared there. So certainly when you take any gi, raise it to the power p to the I to the alpha I, you're certainly going to get the identity element, okay? Because the p to the I to the alpha I is a multiple of the order of little gi. Okay. So that means if we take G1 and raise it to a large power, this power being P2 to the alpha 2, P3 to the alpha 3, Pk to the alpha k. Okay, so we're raising G1 to this huge exponent. So G1 is equal to is G2 times G3 up to Gk. So that's the same as raising G2 up to Gk to that same large exponent. Okay, well, raising that product of group elements to this large exponent is the same as raising each of them to that large exponent and multiplying the results. It's just manipulation of rules of indices. So this is G2 to that large power, G3 to that large power, all the way to Gk to that large power. I'm not going to laboriously write it in each time, but that bracket there is this bracket here. Yeah. But you see, this large bracket, and you can say this for any of the indices I between 2 and k, this large bracket is a multiple of pi to the alpha I. And that can be said for any value of I between 2 and k. So this large bracket is a multiple of the order of each of these elements, G2, G3, and so on. So when you raise an element to the power a multiple of its order, you're going to get the identity. Because raising it to its order gives you the identity, and then continuing to product that identity with itself, which is what you do when the exponent is a multiple of the order. You're just multiplying the identity by the identity loads of times. So this is just a big bunch of identities multiplied together. So it is just the identity. But we've now got G1 to this huge exponent gives you the identity. So that implies the order of G1 divides our large exponent. I will write it out now. Okay, whenever you see an element raised to a certain power giving you the identity, the order of that element must divide that large power. Okay. The order of an element is the smallest possible exponent you can put up here so that you get the identity back. And any other exponent there that gives you the identity, you can only do that by being a multiple of the order. So the order of G1, whatever it is, must divide that. But we already know, because G1 isn't any old element of G, it's a special one, it comes from the first primary component. So we already know that the order of G1 is some power of P1. Okay, but since G1 is in capital G1, the order of G1 is P1 to gamma 1 for some 0 less than or equal to gamma 1 less than or equal to alpha 1. Alpha 1 being the largest power of P1 as an order that you can have inside the group G. But now P1 is a distinct prime from any of those. Okay? But the prime Pi, prime P1 is distinct from all these other primes, P2. The list of primes P1 up to Pk are distinct prime numbers. So we're trying to say simultaneously, the order of G1 divides this, and simultaneously the order of G1 is a power of P1. But now generally that looks wrong. How can a power of a prime P1, how can that divide into, be a factor of, a product of a load of different primes? Okay? You can only divide into a product of a bunch of primes if you are one of the primes, or a power, if you are a power of primes that is a subset of this. So there's only one possibility that this can all still be true, is if this isn't really a genuine power of P1, that if this quantity is actually 1, where the gamma 1 is actually 0. Okay, so this can only happen. The only way to have both of these true is when gamma 1 is 0. So the order of G1 is 1, and so there it can divide that fine. Okay, this 1 divides everything. Okay? The only way this can happen is if gamma 1 is 0, i.e. for the order of G1 is 1, and the only element that has order 1 is the identity element. Okay? G1 is equal to the identity, as the order of G1 is 1 in that case. G1 is 0, which is equal to 1. So what that's saying is, okay, we got lost in some technical details there, but we were trying to prove that the primary components are pairwise as disjoint as they can be, but they only pairwise, in pairs, they only ever overlap in the identity element. So what we did is, well, imagine a situation where you can have any element from G1 written as a product of elements from the other primary components. Now we found that can only happen when you're the identity. Okay? But if one of these pairwise disjoint conditions weren't true, if there was a genuine non-trivial element, a non-identity element that happened to be in two different, happened to be in G1, say, and one of the other primary components, then you could take that non-identity element G1. It appears in one of the other primary components, let's say G4. So this element G1 could again appear in this product here, G4, and that would be a non-trivial element. All the other G's you could choose as the identity. So you would be able to write a non-identity element as a product of elements, one from each of the primary components. Okay? But we've just proved that you can't do that, because we've just proved that in any situation like this, the only way to do this is when you're talking about G1 being the identity element. Okay? So that means that G1, so this implies that for each j between 2 and k, G1 intersect Gj can only ever consist of the identity element. It must consist of at least the identity element because they're both subgroups, but there can never be anything else. So that shows that G1 is pairwise disjoint as much as possible with all the other Gjs, and it's exactly the same argument for any other. You know, there's nothing special about G1. G1 just happens to be the first one appearing in our list. So equally well, you can run the same argument to show that any other of the primary components is disjoint from all the other ones as well. Okay. This applies as well to all other primary components, not just G1. So they are pairwise as disjoint as possible. Okay, we've got a collection of subgroups now that only overlap, any pair of them that only overlap in the identity element. Okay. So this means an internal direct product. Notice an internal direct product I'm talking about can be formed with the GI. Okay. We can talk about the internal direct product G1 multiplied by G2 multiplied by all the way up to GK. This is an internal direct product construction. It will be isomorphic to G1 times G2 all the way up to GK. But there's still a little question over whether it is equal to all of G. Remember, these primary components are certainly not a partition of G. There are plenty of other elements in G who have orders which are products of different primes, products of powers of different primes. So we still got this question, is this internal direct product, does it give you all of G? Or could it possibly only be a subgroup of G? So there's still a question mark surrounding that equal sign on the board. Now, if we look at what he does with his arguments in the book, yeah, I hope I'm not misspeaking here, but I don't find it convincing. And I think it needs something extra, which I can give you. So this is where we get to, this is what I've been talking through. We know the GIs are pairwise disjoint as possible. Hence, they do form an internal direct product. Now here is where he claims to show that the internal direct product is all of G. And he seems to be doing it on a counting type argument. He's going to judge how many elements are in the internal direct product, just the size of it. And he claims that it's equal to the size of G. And he reaches that conclusion because he says the size of it is equal to the product of, all the pi's to the alpha i's. That was our prime factorization of n. So if it is equal to that, then it must be equal to the order of G. Now, he hasn't said anything more about it there. So in order to claim that, first of all, the amount of things in the internal direct product is the product of the amount of things in G1 multiplied by the amount of things in G2, etc. So it is the product of all the things. So I think the only way he can reach this conclusion here is if he's using this fact that the order of GI is equal to PI to the alpha. But he hasn't proved that here. Okay, it's not proved here. The only thing that is proved, if we go back to 13.7, all we did prove here is that if finite abelian group is a P group, and this applies to each of the primary components, they're a P group for a different prime each time. So they are P groups. Well, we know the size of a P group must be a power of that prime. But the question is, it's some power of the prime, but how do we know it's this full power, this pi to the alpha? And I claim that we don't quite know that at this stage yet. All we know is that the size of each of these GIs is some power of P. So if we want to, a counting argument isn't enough at this stage, I think. So we can say the number of things here is the product of the number of things in each one. So it will be a product of powers of P1 times P2 up to Pk. But the question is does it reach up to n? Is each of these exponents actually alpha I? And given what's there on the page, I don't think he's done it, okay? And the reason I don't think he's done it is, well, I mean, I could be wrong, but I'm not, I still think there's a legitimate question about how do you know it's this power, alpha I of Pi? Because the lemma only says it's some power of P. And it's not a, the proof isn't constructive, lemma 13.7. The proof doesn't tell you exactly what the power of P is. All the proof works just by dismissing the possibility that there are any other primes involved. So there's only one prime possibly involved in the size of G, therefore it has to be some power of that prime. So that lemma is non-constructive. It certainly doesn't construct the constructive power. So, okay, let's continue. So an internal direct product can be formed with the G1, G2 up to Gk. So now we want to show a claim that when you multiply them all, you actually get all of G. Because at the moment up here, all we know is that when you perform their internal direct product, you get a subgroup of G. Something certainly contained within G, because these are all subgroups of G, so you're still within the group G, but the question is, how do you get all of G, or could there still be some elements missing? So the question here is, so let A, what we'll do is we'll let X be any element of G. We need to show that X can be written as X1 times X2 all the way up as far as Xk, where Xi is in G. Okay. In the book, he seems to try and establish that by a counting argument, saying that the number of things in this direct product is already the number of things in G, therefore the two sets have to be equal. Because you can't have a subset within another set where the two sets have the same size, well then the subset must be all of the containing set. Okay. Okay, so somehow we have to find these elements. Somehow we have to find these elements, one from each primary component, that multiply together to give any old element X. Now that seems quite daunting at this stage, because X is just any old element of G. We can't locate it anywhere in particular. So we don't seem to have a lot to go on, apart from X itself. And one way to build other elements in the group G is to look at powers of X. And we can do that. Okay. So, yeah, here's how we go about it. Recall N, this number, which is the size of G. This is its prime factorization. Pi distinct prime numbers. Some number of these, K. I equals 1 to K. The integers N divided by Pi to the alpha I. Okay, so these K integers these k integers are paired as a set of k integers are a coprime k set. If you look at any two of them, so here we're talking, so the first one is the product of all the prime powers except the one involving P1. The second one is the product of all the prime powers except the prime power involving P2. Because out of n, we cancel out pi to the alpha I. But that's part of n, but we cancel it out, and that gives us k integers. These form a coprime set, meaning the GCD of n over P1 to the alpha 1, n over P2 to the alpha 2, the greatest common divisor of all of them is 1, okay? Because there's no common factor that's common to all of them. Okay? N is a product of all powers of all the primes P1 up to Pk, but in each time we're cancelling out one of the primes completely. So there's no prime at all that's common to all of them. Yeah? There's no number that divides into all of them. So that means they're coprime. And then we can call on this magical device, you'll remember it from last year, Bezout's identity. Remember, if you've got a set of integers with a certain common divisor, you can find, out of the Euclidean algorithm, you can find a linear combination of them equal to that greatest common divisor. So there exist integer coefficients. I don't think I've used betas yet. Integer coefficient bi such that the sum of beta I n divided by pi to the alpha I, sum of all these, this linear combination can be found that's equal to 1. Okay, so we're making use of some good results from number theory last year. Okay, you got a bunch of numbers that are coprime as a set. There will be a linear combination of them with integer coefficients that's equal to 1. So magically, this x, which of course, remember, is x to the power 1. So we can suddenly write it, instead of 1 here, we can use this huge exponent. So this is all going up in the exponent position. Stop putting in the limits I equals 1 up to k, just well, because it's in the exponent position, but same limits, I equals 1 up to k from the sum. That's fine because x is x to the 1. 1 is equal to this huge thing. So we got this weird linear combination of integers, which at the end of the day is just equal to 1. But we're just expressing it as this really convoluted, long linear combination. So that we can split it up. What is x to a sum of a load of, x to the power of a sum of a load of things? Well, using your usual rules of indices, that turns into a product of things. So this is x to the power of b1 n over p1 to the alpha 1 times x to the beta 2 n over p2 to the alpha 2, etc., all the way to x times beta k to the n over pk. Now I wanted x at the top. Remember, we wanted to show that any x from G was in the internal direct product of the primary components. I wanted an x1 and x2 up to xk, so that when you multiply them all together, you get x. This is it sitting out in front of us. Okay. Here we've got k different elements. Each of them is a certain power of x. Remember, everything is integers. It looks like fractions, but these are all integers. The claim is, if you look at the ith one along here, you get this ith power of x. That's an element from the ith primary component. So note that when you send x to the power of bi n over pi to the alpha I, that number, when you raise it to the power of pi to the alpha I, what do you get? The pi to the alpha I cancels with that alpha I. So when you do power of a power, you multiply the indices. So that will cancel that out. So that will just be equal to x to the beta I to the n. That's equal to x to the n to the beta I. But Lagrange's theorem, remember, n is the size of the whole group G. When you raise x to the power n, you get the identity element. That's Lagrange's theorem. So x to the power n is the identity element. So identity element of some power is just still the identity element. So this number, sorry, this group element, this power of x, when you raise it to the power of pi to the alpha I, you get the identity. That means the order of it is a divisor of this. Therefore, it must be a power of pi. Therefore, this is in the ith primary component. So that implies the order of x to the bi n over pi to the alpha I is a power of pi. So that implies it's an element of GI. So this product here is indeed the one you were looking for. Any element from the group G can be written as a product of things, one from each of the primary components. We've already established that the primary components multiply together to give an internal direct product, some subgroup of G, but then anything, now we just demonstrated, anything from G is in the internal direct product. So the internal direct product is all of G. So this proves to that. This proves that G is equal to G1, G2, to GK as required. So finally, we've reached this stage. So this question mark is gone now. So G is exactly equal to this. So the next lemon to prove will be that we can do the decomposition into direct product of cyclic groups, that we can do that on one of those primary components, and by induction you can do it on them all, and then they all multiply together to give us our giant expression of those cyclic groups multiplied together, direct product. Okay, sorry, I've gone a few minutes over there. So, but any queries?